So today we will discuss about okay. So today we will discuss about the DC motor. Okay. So today's topic is based on this DC motor principle of operation, constructional details. Okay, and back EMF. What is the significance of back EMF? So today we'll discuss about these three topics. Okay. So for the introduction. So as we have discussed in the early first class only, the DC machines are of two types. One is the DC generators and DC motors. So the DC generators will convert the mechanical energy into electrical energy, and the DC motors will convert the electrical energy into mechanical energy. So in the first unit, we have discussed completely about the constructional details of DC generators, principle of operation, and the voltage and current relationships. And also we have discussed about the characteristics. So depends on the characteristics. So we can go for the different applications for the machines. Okay. So just can you wait for only 1 minute? Can you see this now?
Yes, sir.
Okay. So the DC generators will convert the mechanical energy into electrical energy, and the DC motors will convert the electrical energy into mechanical energy. So, in order to understand the concept of operating principle of a DC motor, so we need to see that how the force will be exerted on a current carrying conductor which is placed in a magnetic field. So, the basic principle of operation of a DC motor is depends on the mainly a straight conductor is placed. The straight conductor is placed in a magnetic field which is produced by a permanent magnet. Okay, and that conductor is carrying a current, and due to the presence of the magnetic field produced by the field winding, and also with the magnetic field produced by the armature conductors, so there is a interaction between these two fluxes taking place in a DC machine, and it exerts a force on the conductor or on the armature. So because of this force, which is called as a twisting force, which is acting on a circular path, then it exerts a torque. So your armature is rotates. Okay. So for understanding of this, how it is taking place. So let us assume that uh, let us assume that I will take some force on it. Here, this is a North pole. Let us assume this is a south pole. Okay, so this is a north pole and this is south pole, which is present in the stator. Okay, and this is producing the required amount of the magnetic field. This is producing the required amount of the magnetic field like this. Okay, and now I will consider one conductor which is placed in the magnetic field. This conductor is placed in the magnetic field. Okay, and this conductor is not carrying any current. Okay, and next I will take another case here, and in this case we can assume that this is a north pole again, this is the south pole. So this is not developing any magnetic field, is not produced, but here in this there is a conductor is there, and this conductor is carrying a current. So whenever this conductor carries the current, okay, so whenever this conductor carries the current, then around this conductor some magnetic field is developed like this. Okay, so some magnetic field is developed by this conductor. Then what is the direction of this magnetic field, which can be obtained by the right hand thumb rule? So the direction of this flux can be obtained by the right hand thumb rule. So here just you take the right hand, your right hand, okay, then can you see my video?
Presentation is not working, sir.
Yes, just presentation పైన ఒకసారి క్లిక్ చేసి చూడండి.
Yeah, కనబడుతుంది, sir.
Can you see my video?
Yes, sir.
కనిపిస్తుందా?
Yes, sir.
Okay. So just you see that this is the thumb, okay, and thumb is indicating, okay, this thumb is indicating the current towards the conductor, and our fingers will indicate you, the fingers will indicate you the direction of flux. Direction of the flux can be obtained by like this. Okay, if you see that the current is coming outwards, so the direction will be in an anti-clockwise direction. If the current is flowing into the plane of your conductor, then your fingers indicates the direction in the clockwise direction. Okay, is it clear?
Yes, sir.
Okay, so now can you see my PPT now? Just you click on my PPT.
Yes, sir.
Can you see it?
Yes, sir. కనబడుతుంది.
Okay. Just a minute. Hello.
Sir. Okay.
So here, just you see, whenever this conductor is carrying the current towards the plane, then the flux direction will be like this because it is in the clockwise direction. So this will be downwards like this. Okay. So if this conductor is carrying a dot, then the direction of the flux will be in a opposite direction. Okay. Okay, now.
Okay, sir.
Then next. Now let us assume that instead of taking separately the magnetic field and the conductors which are carrying the current. So if both are present at the same time, if these both are present at the same time, then we'll see how it will be. So I will take the another case now. Here this is a North Pole again, and this is a South Pole. Okay, and this is carrying the flux. This is the main flux which is produced. Okay, and this will be like this. This is the main flux which is produced. Okay. And now I will take the conductor in the magnetic field. What I'm doing, the main principle of operation is if a straight conductor is placed in a magnetic field which is produced by a permanent magnet. So here just we are assuming that this is a permanent magnet, and then in this we are producing a current conductor, current flowing through the conductor, and therefore I'm placing a conductor here, and this conductor is carrying the current. And this conductor is carrying the current, and now because of this current flowing through the conductor, then some flux will be developed, and this flux is like this. Okay, so if the flux is in this fashion, now this is flowing upwards. Here this is like this. Now to the right side, this flux direction is downwards. Okay, so just what you observe here is, what you can observe here, to the left hand side, to the left side, the flux which is produced by the main field flux, main feature, both
Sam,
are
you
in
was
opposite
break out
direction.
on sir.
Hello,
Sir,
hello,
sir.
ఇప్పుడు వినిపిస్తుందా క్లియర్ గా?
ఇప్పుడు ఏం వస్తుంది సార్?
వినిపిస్తుంది, ఓకే. So here the flux which is to the left side of this conductor, the main flux is in the downward direction, and but your flux which is produced by the armature in the opposite direction to the main flux. But to the right side of this conductor, both armature flux in the downward direction and also the main flux both are in the downward direction. And therefore, the flux density to the right side of this conductor is higher as compared to the flux density to the left side. And therefore, now the resultant flux which is produced by the two fluxes can be in this fashion. To the conductor here, so I will consider this as a conductor. Okay, so here this is a conductor what I am considering. This is carrying the current, and therefore what is the net flux? I can show it by the lines. So the net flux will be like this. So this flux is in this direction, and there is no flux which is developed because I'm taking the three lines here. So you can see that the net flux will be in this fashion for this North Pole and South Pole. And therefore, this flux lines, which looks like a stretched rubber, okay, then this will exert a high force on the conductor, and this conductor will be moved to the right side. Okay, so here this is a flux weakening takes place to this point here. The flux weakening takes place to the left side of the conductor, but flux is more flux is gathered here. So this is a more flux which is gathered here. Okay, but at this side, the flux is weakened, and therefore this flux lines looks like a stretched rubber, and it will exert a force on the conductor, and this conductor is will rotate or try to move in this direction. So this is called as a force which is developed, which is known as the direction of force. So this is in the direction of the this is the direction of the force. Okay, is it clear? Is it clear? Any doubts?
Yes, sir. No doubt.
So the final value will be like this. Here, this is a resultant flux which is looks like. Okay. So the same case what we are taking here. In the case one, this is the interaction of the two fluxes. Okay, main flux and the armature flux is taking place, and then now it is to the right side of the conductor, crowding of the flux is taking place, and this crowding of the flux will be forcing the conductor to move. Okay, so this is called the development of the force in the DC motor. Whenever this force is acting on a circular path, normally here your armature will be in a circular path. Okay, and therefore here this is the radius of your armature, and then it is exerting the force on the rotor. So that is nothing but the development of the torque. Okay, so torque is nothing but the force. I can take this as capital F. Okay, and we will consider this as a small r. Okay, so this is the radius of your armature. So F into R. This is the torque which is developed in a motor. Okay. So now we'll discuss this in detail. So as shown in figure 1. So what is the figure 1? Okay, this is the interaction of the fields is taking place, and it is a resultant field. So as shown in figure 1, the flux lines produced by the magnet and the conductor are in opposite direction to each other at the left side of, and hence they cancel each other. Okay, and therefore there no flux lines at the left side will be uh, reduced. So that is the number of flux lines at the left side will be reduced, but at the right side the individual fields are in the same direction. The individual fields, that is a field produced by the armature and also the field produced by the magnets, are in the same direction, and hence they will add and strengthen each other, and therefore the number of flux lines at the right side will increase. So because of this increase, there will be some force which is developed. Okay, and that force is given by the magnitude of the force which is developed is given by the formula BIL, where B is the flux density and I is the current passing through the conductor, and L is the length of the conductor. Okay, so the amount of force which is developed by the current carrying conductor which is placed in the magnetic field is given by BIL newtons. This is a units are newtons. Normally we represent by the capital N. Okay, where B is the flux density which is produced by the magnets. Normally we use electromagnets. So now here for the simplicity purpose we are taking the permanent magnet, but these magnets must be electromagnets. And capital I is the current which is flowing through the conductor, and L is the length of the conductor which is under the influence of the magnetic field. So this is the amount of force which is developed in the conductor which is carrying a current and it is placed in the magnetic field. Okay. So now, what is the direction of the force? So the force is developed here. So the direction of the force, which is depends on the armature winding and also on the direction of the force which is excited by the current carrying conductor is given by the Fleming's left hand rule. So in previous case which we discussed for the DC generator, the direction of induced EMF we found out with the help of the Fleming's right hand rule. Okay, but the DC motor, for the DC motor, the direction of the force which is developed can be found by using the Fleming's left hand rule. So the statements of this Fleming's left hand rule is, okay, if the first three fingers, the thumb, forefinger, and the middle finger of the left hand are held mutually at right angles, so these three must be held right angles to each other. Okay, and the index finger, that is the forefinger, index finger indicates the direction of the magnetic field. Indicates the direction of the magnetic field, and the middle finger indicates the direction of the current flowing through the conductor, and then the thumb indicates the direction of the force exerted on the conductor. Okay, so the index finger indicates the direction of the magnetic field, and the middle finger indicates the direction of the current flowing through the conductor, and the thumb indicates the direction of the force which is exerted on the conductor. So this can be shown here. So this is a Fleming's left hand rule where this finger, this is the index finger which is indicating in the direction of magnetic field. Okay, and this middle finger is indicating the direction of the current which is passing through this conductor. So this is in this direction. Okay, and this thumb is indicating, the thumb is indicating the direction of the force which is exerted. So force is exerted on the armature and it is trying to rotate in the anti-clockwise direction. So this rotor is trying to rotate in the anti-clockwise direction. Is it clear here? Yes?
Yes, sir.
So just for simplicity purpose, I will take the different cases here. So this is a south pole and this is the north pole, let us assume, and this is producing the flux like this. Okay, and this is a conductor which is carrying current. Okay, and here the flux lines are in the clockwise direction. So for the left side, there is a crowding of the flux takes place, and therefore force will be exerted in this direction. Okay. Now if I will change the direction of the current which is passing through the conductor. I'm not changing this one. I'm not changing the position of your North Pole and South Pole here. This will be same like this. Okay, and here this is the current, but the current flowing through the conductor, current flowing through the conductor is dot. Okay, as this is a dot, then the direction will be in the clockwise, anti-clockwise direction. The net flux produced will be in the anti-clockwise direction, and therefore the force exerted by this conductor is in a opposite direction like this. Okay, just you see the difference between the first case and the second case. In the first case, the conductor is carrying the current into the plane, and therefore the flux force which is developed in the clockwise direction. Now the magnetic field is kept constant, but the current carrying conductor, the direction of this current I am changing, and therefore the direction of your force is reversed. Okay, and then the same case here, I will take that, I will change the direction of the magnetic field now. I will interchange the positions of North Pole and South Pole, and therefore here the flux lines will be like this. These are the direction of flux lines, and in this I am placing the conductor. Now you assume that this is a conductor which is carrying the current, and therefore what is the force exerted now? The flux will be in the clockwise direction. So for this clockwise direction, the right hand side will be having the crowding of the flux, but the left hand side weakening of the flux. And therefore the force will be exerted to the clockwise, anti-clockwise direction like this. Okay. In the other case, this is the North Pole and this is the South Pole again. The same flux is producing here. So the direction of flux is from north to south, and here the conductor is placed, and this conductor is carrying a current outwards. Okay, and therefore the flux will be in the anti-clockwise direction. The flux is in anti-clockwise direction here. Okay, so as the flux which is produced is anti-clockwise direction, and therefore the crowding of the flux takes place to the left side, and weakening of the flux takes place to the right side, and therefore it exerts a force to the clockwise direction. Okay, so this is a way of changing the direction of your armature of a DC motor. Okay, either you have to change the field direction, or either you have to change the direction of the current through a conductor. Then you can change the direction of the motor for it. Okay, so if I want to change the direction of a DC motor, I need to change either direction of the field, the magnetic field, or you can call it as a main field, or the second one is you need to change the direction of the current which is passing through the conductor. Current through conductor. So these are the two cases you can change any one case so that the direction of your force and similarly the direction of rotation of your armature can be changed. Is it clear? Any doubts in this?
Clear, sir.
Okay, next. Now we'll see the windings in a DC machine. So already we have discussed the same windings for DC generators. The same windings can be used in case of DC motors also. Okay. So in DC machines, there are two types of windings are available. One is the field winding and second one is the armature winding. And the field winding is placed on the stator, so it is a stationary. And the armature winding is mounted on the rotor shaft, so it can rotate freely. So this construction is same as for the DC generators also. Okay, so to operate the DC machine as a motor, the field winding and armature winding is connected across the DC power supply. Because in case of DC generators, we have seen that the field winding is excited for the separately excited generators, and in case of self-excited generators, because of the residual flux, some kind of voltage will be developed, and that voltage we call it as a residual voltage. And that residual voltage will produce a small amount of current in the machine, and then that small amount of current is added to the residual flux, so it will build up a voltage. So again, because of this voltage, the current will be increased. Because of the increase in current, again the voltage is increased. So this is a cumulative process where you are producing the required amount of voltage in a DC generator. Okay, but in case of a DC motors now, we need to produce the force. So both the windings, the field winding and armature winding, has to be excited. So these two windings are connected to the DC power supply. Okay, so now we'll see the principle of operation again. Already we have seen, but once again we'll go through this. So the principle of operation is consisting of, when a current carrying conductor is placed in a magnetic field, it experiences a force. Okay, so in case of a DC motor, the magnetic field produced by the field current, that is the current flowing in the field winding, and the armature winding plays the role of a current carrying conductor. So friends, with the help of a DC power supply, we allow the current to flow through the armature winding, and therefore this armature winding experiences a force and it starts the motor to rotate. Okay, and this is the construction of a DC motor. So it is similar to your DC generator. Again, it consisting of a stator and the rotor. So this part, this complete outer part is called as a stator. Okay, and this inner part is called as the rotor. The stator consisting of, again, yoke. Okay, this one, yoke, and next it consisting of poles, and then pole 2, and next the field winding on the this field winding on the stator. And next one, to the rotor, it consisting of the armature. Okay, so here this is the armature, and next on the armature we are having the armature winding. This armature winding is placed on the armature circuit, and this armature conductors are connected to the commutator, and also this complete commutator assembly is connected to the brushes. With the help of these brushes only, the input supply is given, and this complete part is connected to the shaft. Okay, so it is having a some shaft here. So this shaft is connected to your mechanical load. Okay, so this is the main cut view construction view of a DC motor. Now the important parts of this DC motor are, we have seen here, this is a yoke, okay, and the poles and the field winding which are placed on the stator, and armature, a commutator and a brush assembly which is placed on the part of a rotor circuit, and also the brushes. This is a part of a rotor circuit and this is a part of a stator. So this is the part of yoke, field winding, and poles are the part of stator, and the armature and the commutator brushes are the part of the rotor. And the yoke, it acts like an outer support for the DC motor, similar to your DC generator, and it doesn't allow the flux to flow out. Okay, so it will protect the flux which is developed by the DC motor to be present only inside of that part, and it is also providing the mechanical support for the poles. So this is the function of a yoke, and the next, the poles. So the poles of a DC motors are of electromagnetic type because these are excited by the field winding. Okay, so the field winding is wound over the poles, therefore it is acting as electromagnets, and these poles will produce the required amount of the magnetic flux when this field winding is excited. And the next part is the field winding. The coils which are wound around the poles are called the field coils or field winding, and they are connected in series with the other form of a field winding. Then whenever the current passing through the field winding, then the magnetic flux is produced in the air gap between the poles and the armature. And next part is the armature circuit. So armature is of a cylindrical drum. So already we have discussed in detail about all these parameters in case of a DC generators. So the same construction which can be used for the DC motor also. So a DC machine can be operated as a DC generator or DC motor. So depends on your input supply. That's why here I'm going in fast. Okay, so the armature is a cylindrical drum mounted on a shaft, which is having a number of slots. On these slots, we place armature conductors, and these armature conductors will carry the current whenever these are excited. And again, here the commutator, it is a cylindrical drum mounted. This same uh, construction as the armature, and it is also mounted on the shaft along with the armature core, and it is also collects the current from the armature conductor and pass it into the external load via brushes. Okay. So in case of AC motors, it will convert DC to AC. So for the purpose of providing the torque and the brushes, okay, so which are connected to the commutator segment. So whenever the commutator is rotating, it is touching the brushes, and the current which is developed by this and commutator segments will be collected by the brushes. Okay, so these are the some parts of points regarding the constructional parts of a DC machine. Now let's see the back EMF. So back EMF is nothing but again because of change in flux which is linked with the conductor, again an EMF is induced in the conductor, and that is known as a back EMF. Okay, so we'll see in detail about this. So when an armature winding of a DC motor starts rotating, so the armature winding of a DC motor or armature conductors of a DC motor starts rotating in the magnetic field produced by the field winding. It has the lines of magnetic flux. So it is similar to your DC generator, and therefore the DC generator action is also taking place in the DC motor. So hence, according to the Faraday's laws of electromagnetic induction, there will be an induced EMF in the armature winding. And as per the Lenz law, this induced EMF acts in opposite direction to the armature supply. Hence, this induced EMF is called as the back EMF, and it is denoted by the EB. Am I clear? So can you see my PPT? Is it moving? Is it moving?
Yes, sir.
Okay. So in my mobile, it is not moving. That's why I'm asking you. Okay. So
ఓన్లీ వన్
whenever,
పాయింట్ ఉంది సార్,
yeah,
ఒకటే పాయింట్ ఉంది సార్.
అవునా, అది అందుకని అడుగుతున్నాను నేను. Just now see. మీకు కూడా ఒకటే పాయింట్ ఉందా?
ఎస్ సార్.
Yes, sir.
ఇప్పుడు చూడండి, ఇప్పుడు వస్తుంది.
యా ఓకే సార్, ఇప్పుడు 3.
Okay, so in the first case, whenever when an armature winding of a DC motor starts rotating in the magnetic field. In previous case, what we have taken, so this is the north pole and this is the south pole. What we are assuming here, it is having the magnetic field, okay, and in this magnetic field we are placing the conductor, and this conductor is carrying the current. But now, because of this, whenever this is rotating in a clockwise or anti-clockwise direction, in this process, this conductor is also cutting your main field flux. So as per the Faraday's laws of electromagnetic induction, so whenever conductor cuts the magnetic field, an EMF is induced in this conductor. Okay, so this induced EMF, as per the Lenz's law, it has to oppose the direction of your armature supply voltage. So hence, this is called as a back EMF. So this is denoted by EB, and the equation for EB is also same, because the nature of the voltage which is developed is same as per the DC generator. So this is also same as phi z n into p by 60A, which was developed for the DC generator, which will be developed in DC motors also. Am I clear here? So in DC motors also, there is a action of, in DC motor also there is a action of DC generator. So DC generator is nothing but whenever conductor cuts the magnetic field, an EMF is induced in that. Okay, whenever conductor cuts the magnetic field, an EMF is induced in the conductor. So in this case, that induced EMF, we are calling it as a back EMF. So this is
సార్ వాయిస్ వినబడట్లేదు సార్.
ఎస్ సార్.
కనిపిస్తుందండి? స్క్రీన్ కనిపిస్తుందా?
షేర్ అవ్వట్లేదు సార్ ఇంకా స్క్రీన్ షేర్
శ్రీనివాస్
స్క్రీన్ షేర్
కనిపించట్లేదు.
అవ్వట్లేదు సార్.
స్క్రీన్ కనిపిస్తుందా?
లేదు
లేదు
సార్.
సార్.
పవర్ పోతుంది. Okay, then Srinivas, shall I stop here?
ఓకే సార్.
సార్
ఇక్కడ స్టాప్ చేసిన మొబైల్లో వస్తుంది, ల్యాప్టాప్లో రావట్లేదు. సో టుమారో విల్ డిస్కస్ అబౌట్ దిస్.
ఓకే సార్.
ఓకే సార్.
ఓకే సార్.
ఓకే,
థ్యాంక్ యూ సార్.
థ్యాంక్ యూ సార్.
థ్యాంక్ యూ.